Hybrid search does not have to mean Elasticsearch plus a vector database. Qdrant FastEmbed gives you sparse and dense retrieval in one Python path. You'll learn the shape of a workflow that ingests hybrid documents and retrieves fused lexical plus semantic matches. I'm Professor Pi, teaching search and IR with simple Python. Hybrid retrieval solves a very practical tension. You want exact keyword guarantees and broad semantic recall at the same time. In support desks or compliance work, a keyword hit can be non-negotiable, while semantic matches find paraphrases and intent. People reach for hybrid search when dense-only systems miss legally required phrases, or sparse-only pipelines miss synonyms and intent. Qdrant FastEmbed bundles both channels in one place. Rather than juggling a vector DB and a separate sparse index, FastEmbed stores a dense slot and a sparse slot inside the same collection. That keeps IDs, payloads, and model outputs aligned, and makes fused retrieval far easier to reason about. The core idea is simple. Each document gets two vector views. One dense embedding captures meaning. One sparse vector behaves like a keyword scorer. At query time, we ask both channels and combine their votes, so exact phrases and semantic neighbors both count. We'll build a compact demo that shows the whole flow. You'll see collection setup, ingest two toy documents with both vectors, run a sparse-only probe, run a fused RRF search, and finish with a guarded hybrid query that respects metadata. That should make the pattern clear so you can scale it safely. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we need a place that holds both dense and sparse slots, and that locks the dense dimensionality expected by FastEmbed. This snippet initializes Qdrant's in-memory instance with dense and sparse vector slots ready for FastEmbed ingestion. Keeping lexical and semantic indexes in separate stores makes it easy to lose alignment on vector sizes or payload schema. By calling QdrantClient memory, we spin up a disposable engine, name the dual vector channels via dense name and sparse name, and lock the dense dimensionality with models.vectorparams size equals 384. Models sparse vector params activates the sparse slot without any external BM25 service, so you can feed FastEmbed sparse emitters straight into the same collection. The final collection ready flag confirms Qdrant has accepted both vector configs, giving you a single data store for subsequent hybrid steps. Now that the index shape exists, we load documents so every point gets both vectors and the database can keep them aligned. This example loads two toy documents through Qdrant's FastEmbed integration, so dense and sparse encoders stay perfectly aligned. Manual embedding pipelines tend to drift, because batch scripts forget which model produced which payload, especially when lexical boosts live elsewhere. The loop enumerates cases, builds models document instances for D model and S model, and assembles named vectors keyed by dense name and sparse name. Client.upload collection then pushes both vector types plus payload metadata and IDs in one transaction, letting Qdrant run FastEmbed inference lazily. Points loaded tells you the collection now holds the two demo records, giving you a minimal yet dual channel index to test against. With data in place, run a sanity check on the sparse side to make sure keyword hits actually survive. This code probes the sparse retriever to verify that exact compliance language wins when you route a query through sparse name. Teams often discover their hybrid stack can't guarantee keyword hits once dense approximations take over, which is painful for audit text flows. Client.QueryPoints runs a models document built with smodel, and using sparse name ensures Qdrant executes the BM25-like scorer rather than the dense channel. The limit equals 1 cap keeps latency predictable on longer lists, though raising it would show more lexical ties if you have them. The printed sparse hit and score reflect that the compliance tagged point surfaced with high lexical relevance, validating your sparse side. Next, we ask both channels and merge their candidate lists into a single ranking. This snippet fuses dense and sparse prefetches with models.Fusion.RRF, so you can see hybrid scoring in a single call. Relying on only one channel makes intent coverage brittle. Dense only misses regulated phrases, while sparse only ignores paraphrase support tickets. By defining dense query and sparse query once, and bundling them in hybrid prefetch, Client.QueryPoints can make the dense name search propose semantic candidates, while the sparse name path contributes lexical votes. Reciprocal rank fusion rewards whichever vector jumps high in its own list, and altering limit from 2 upward lets you inspect deeper blends at the cost of more downstream sorting. Hybrid tags and the top score output show both records sorted by the combined signal, demonstrating that Qdrant merges lexical safeguards with semantic recall. Finally, add a metadata filter so compliance tags or regional gates can veto semantically close but out-of-scope records. This example adds a metadata gate to the hybrid query so compliance-only hits survive even when dense neighbors look tempting. Hybrid retrieval without filters easily leaks semantically close records that violate regional or regulatory scoping, which undercuts downstream answer guarantees. Models filter with models field condition ties the query to tag equals com, and Client.QueryPoints reuses hybrid prefetch so both dense query and sparse query still drive scoring. If you loosen the filter value, you widen coverage, but tightening it keeps latency steady because Qdrant prunes results during traversal rather than post-processing. The printed, filtered value and score confirm the fuse search respected the compliance guardrail while keeping the sparse strength in play. In this toy demo, the pattern maps directly to larger systems. Dual vectors stored once, retrieval in a single call, and fusion inside the database so you don't manually merge lists. For production, you'd swap the in-memory client for a persistent Qdrant deployment, and scale collection size and fusion depth to taste. Recap. Keep dense and sparse channels together in one collection, so IDs and payloads stay aligned. Reach for this when you need both exact keyword guarantees and semantic recall in the same query. One caveat: fused ranking can surface out-of-scope dense neighbors unless you add metadata gates or strict lexical checks. Next step: tune the fusion depth or weighting. Raise the reciprocal rank fusion depth or change the weights so semantic or lexical votes dominate. Then measure how hits and latency shift. If short, practical IR helps, subscribe and watch the IR videos.